We are really delighted to be able to share today some of the exciting work that we have going on at MSU and try to provide a little bit of an explanation in terms of really what quantum computing is. Quantum computing is a very complex topic. It is often represented by this cat. You see this box here with Schrodinger's cat in it. We're not going to go into the details for that because Schrodinger's cat is a paradox for quantum mechanics, and it helps some people understand quantum mechanics, but for many people it makes it more confusing. And so I'll kind of leave that up to you, but we do have a lot of pictures of cats scattered throughout. Just know that that is a representation for quantum mechanics, and encourage you to read about that. So as Philip mentioned, we are joined here today with Andrew and Johannes, and they are associate directors for a new center that we have in quantum computing science and engineering, and we'll tell you more about that a little bit later on in our presentation. Now, before our news topics have changed now much more to COVID presently, before that, you would see a lot of news about quantum computing. It was in all types of magazines and newspapers, on the internet, in magazines like The Economist, and my apologies. Unfortunately, I can't see with our current format. I can't see. I hope you can see the pictures on the right, but I cannot. Corey, I don't know if we can fix that or not. Oh, you guys can see them? Okay, great. But truly, quantum is all over the place. And this beautiful picture on the right here is Johannes's son actually looking at this book called Quantum Physics for Babies. And so indeed, quantum is all over the place. One of the things, if you get inspired from this presentation and would like to try out a quantum computer, there are actually a number of quantum computers out there now, and one of them is available to the public. It's through IBM, through this website. And through this website, you can have the opportunity to try your hand at quantum computing and be one of the early adopters of this new technology that is certainly emerging. Also, there are quantum games out there these days. And if you have kids or grandkids, or if you are a big Minecraft fan, you can really kind of take that up a notch. There's actually a quantum mechanics or a quantum computing version of that you can try out called QCraft. It's actually quite interesting, but it doesn't move quite as fast as Minecraft. Now, when we talk about quantum computing, one of the things we really want to talk about is really kind of looking back a little bit at the future of computers and why computing. Our talk is called Quantum Leap, and the reason for that is truly to achieve quantum computing, we have to make some major advances in terms of science as well as technology. And so Johannes will talk about some of those in a bit, and Andrew will talk about some of the rationale for that. What I'm going to cover here is just a little bit of the history. I'm going to take a step quite far back to the early days of computing. The early days of computing were very much needed, and this was around the time of World War II. And one of the challenges was that there were a lot of basically these artillery trajectories that were needed to try to predict the pathways of the artillery. And what was needed was a much faster way to generate these tables. This was really a work in many years of making. This was basically kind of the second computer. It was the ENIAC, the electronic numerator, integrator, and computer. And the capabilities of this, it did allow those artillery trajectories to be computed. But if you note here, the capabilities were not very significant compared to even a dollar calculator that you can purchase these days. You can see that the capabilities were basically just, you could have a positive sign or a negative sign in a number. You could do greater than or less than, add, subtract, multiply, divide. And you could only store up to 20 10-digit decimal numbers. And when you think about it, that really is not very much. And you could do square roots as well. But what was most remarkable, I think, is the fact that this was a 30-ton machine. It had 30 separate units, 19,000 vacuum tubes, 1,500 relays. It was a very huge machine to do what we think of these days as being quite simplistic in terms of calculations. And the control was so complicated, we couldn't just go to a keyboard. We actually had to change the external hardwiring of the system. So quite remarkable. And I think what was even more remarkable is that this system was considered to be the most complex equipment ever assembled to that date. And when Johannes starts talking about the quantum computer, I want you to think about this, think about the size, and think about, the complexity of this, because we're basically at that again, and you'll see shortly. Certainly advances were made. That was in the 1940s. In the 1950s, what came about was a different system called the EDVAC, the Electronic Discrete Variable Arithmetic Computer. And the capabilities were much improved. You could actually store instruction tape. You could have that as your memory, your way of doing memory, and it was much faster. The instructions could be issued at electronic speed. It was not quite as large. It was still quite large, 7 feet tall, 500 square feet of area. And again, you had to change the external hardwiring of the system. Fast forward about 15 years or so was a system called the UNIVACs, the Universal Automatic Computer. Now, this was actually the first capabilities here were the first modems, the first remote access, but you can see here also an enormous machine, over 2 tons. And in 1968, the price tag on that was $1.6 million. It was a 1.3 megahertz system with one half megabyte RAM, 100 megabytes of hard drive. And you can see here the comparison. If any of you have an Apple 5 watch, it's 850 megahertz, 1 gigabyte, of RAM, 32 gigabytes of storage. And, the price tag's a little bit less. It is expensive, but at least it's not, $12 million. So indeed, we have advanced quite a bit. And the control for this were instruction cards for programming. I remember my mother used actually this type of computer, and she would come home with these boxes of cards, and they were all numbered. And some of my colleagues that are a little bit more senior have told me stories about dropping these boxes of 2,000 cards and trying to put them in order because every instruction came on a different card. Just absolutely remarkable. It was a huge achievement from trying to do hardwiring, but it was still a real big problem if you dropped a box of these cards and it was your whole program out of order. MSU actually entered the scene in the 1950s, 1956 to 1957. And it was basically a system that was kind of like the EDVAC, not the punch card system, but the system just before that. And MISTIC is the Michigan State Integrated Computer. And MSU had really tried to, they had tried to get funding for it. And what happened was they had lost, unfortunately. They tried to compete and the military had gotten, one of the military labs had gotten the contract instead. However, a few persistent faculty had really encouraged the president to invest in a new computer, at the very first MSU computer. And the president of the time was Johannes, and quite a remarkable president at MSU, and we have a number of professorships named after them. I'm fortunate to have one of those, so very much appreciate the support for that. But Johannes decided to invest in this computer. And it wasn't a matter of just purchasing a computer and there it was on the floor. It took them over a year. It was almost 2 years to basically put this together and get it operational. What I find pretty interesting, it's a little bit smaller than the machines I already talked about. They're about 10 feet tall, 11 feet long, 2 feet deep, and still 8 other major components, quite big. But it was a system that had a compiler. It could change programs with other computers, which was quite nice. And it could be used remotely. So modems, it could be used via phone. So quite nice. But what I find pretty interesting is this picture on the right. This picture on the right is quite interesting in the fact that it was chemical engineers, folks in agriculture, folks in the dairy, in dairy at MSU, all of these different groups and faculty and students were engaged in using this from the very, very start. And so this was not just a system for computer scientists or mathematicians or physicists. It was truly all over the map in terms of the fields that really made use of computers early on. And these timings on the right are actually timings that are from the late 1950s. It was 1959. And so that was quite remarkable to see the computer embraced so quickly at MSU. And that tradition has certainly continued at MSU. We have really come a long way. you know, as I've already illustrated, some of these very old, very large computers to some of the amazing technology that we have today, everything from traffic lights to you name it, you know, so many things are indeed computerized. And of course, I'm going to turn it over now to Andrew, who can talk a little bit about where we're at in terms of the history.
Thank you, Angela. So over time, we've all heard about Moore's law. There you go, Angela. We've all heard about Moore's law, and what Moore's law really tells us about is the number of transistors that we can fit in a computer as a function of time. And for a very long time, the number of transistors we could fit in a computer happened because we were making things smaller and smaller and smaller. So we're basically putting transistors in the same space, but as before, but more of them. And really, the number of transistors is important because it's related to the actual computing power. It's how much you can do with the computer. So if you want to go to the next slide, Angela. Next, there you go. Thank you. So as transistors had gotten smaller and smaller and smaller, and we packed them in smaller and smaller densities, they reached a point at which, due to quantum mechanics, we actually couldn't really fit more transistors in the same space and have them work the way that we want them to. And so what ended up happening is, really the way you make a computer faster is you make the transistors closer together. And when we couldn't make them closer together, that's when the computer stopped getting faster. They just started getting bigger, right? You have your desktop, it might have 8 or 16 cores in it. Your phone has like 4 or 6 cores in it. That's because to make things faster, we now had to put more compute power, more cores in there, instead of actually putting more transistors in the same core, because we couldn't make them smaller anymore. And so there are problems that this leads to. So for example, a lot of the calculations we were interested in doing, we could count on Moore's law of making that calculation faster because the computer got faster. And at some point, when the clock speed stopped getting faster, we couldn't count on making that calculation faster anymore. We could only do bigger calculations. And so if you want to go to the next slide, Angela. So I'm going to mention one example of a calculation we would like to do faster, but we can't because the clock speed has plateaued. If you think about, there's something called a Carrington event. It happened in 1859, and it's a solar flare, and it's a big solar flare that impinged on the Earth. And so what happens is, when a big solar flare, that's hot gas coming from the sun that's been ionized, flying towards the Earth, if it hits the Earth has a magnetic field, and those charged particles get trapped in the magnetic field. And so this big picture on the right that you see is the aurora borealis, but it's specifically due to a solar flare having hit the Earth. This is a small version of a Carrington event, not a very big one. And what you're seeing there is actually the charged particles that are trapped in the ionosphere are creating certain events that create light. And so you're literally seeing where the charged particles are. Now, the problem is, when those charged particles get trapped in the Earth's magnetosphere, they bounce back and forth between the poles. And if you have a lot of them, like a current in a wire, that's a lot of current moving back and forth between the poles. And then that can inductively couple with telegraph wires. This picture down on the left is to point to the fact that in 1859, what happened was there was this giant solar flare. It created this huge amount of current in the ionosphere that then led to telegraph machines blowing up. And why do we care about that now? If that happened now, that would have the same effect on our power plants, which is really a bad thing. So we'd love to do this calculation faster so we could do better predictions. It's called space weather modeling, but we can't. We're really sort of stuck because the computers can't get faster. So that leads us to looking for a new paradigm, and that one really exciting new paradigm that MSU is excited about and invested in is quantum computing. And with that, I'm going to hand it over to Johannes.
All right. So, great. Yeah, as Andrew says, we really need a lot of new paradigms in computing. Quantum computing is just one of those examples, but it's one that I'm particularly excited about, and hopefully I'll be able to convey some of that excitement to you all, and a little bit of why we might want to try to use quantum physics and quantum mechanics to make computation better. So real quick, Angela and Andrew, you can be my guinea pigs here. You can see the slides, I'm guessing? Great. Okay, so that hopefully means that everybody else can as well. So like Andrew said, you know, I view kind of quantum computing as one of the next stages in the human evolution of computing. You know, it's one of the most exciting from my perspective, because I'm a physicist and I like playing around with quantum physics in my day-to-day life, and my students and postdocs do as well. But it's you know, the ideas have been around for some time. The original ideas came around in the 1980s. Richard Feynman had these ideas, and it's been long understood that quantum mechanics itself is a really hard computational problem. Like, trying to understand how nature works at its most fundamental level is difficult. The laws of quantum physics are computationally difficult inherently. But because it's hard to understand, it also means it gives us some power to try to do some computing things better. So, but before we get into the excitement and all that stuff, I just want to give like a little bit of a very hand-wavy primer on what a quantum computer is, what the basic elements are, why, you know, what are the weird things that this gives us. And so what I want to start with is what is the basic element of a quantum computer? It's this thing called a qubit. And that's in contrast to the basic element of a regular computer, like in your laptop or your iPhone, which is a bit. So a bit in your laptop or your iPhone can be, you can imagine it's just a switch or something that can be in one of two states. So it can be on or off. It can represent two pieces of information, 0 or 1. That's the basic computational element. There's lots of ways that those kinds of things can be, you know, vacuum tubes can be used to implement bits. You know, holes in punch cards can be, you know, encode information in this way. Transistors today, voltages on transistors encode this kind of information. Now, what I want you to have in mind for this bit in this analogy is just a light bulb. So it can be on or off. You know, it can be turned on or it can be turned off. And in a quantum computer, you don't have a bit. You have something else that encodes the information. It's called a qubit or a quantum bit. And again, a qubit can be on or off. But most importantly, a qubit can be both on and off at the same time. So Angela has this really wonderful analogy that with this light bulb. And that is that, imagine that, you know, a classical computer is your light bulb switch, can be on or off. But a quantum computer allows you more capability. It's like having a dimmer on the lights in your house. You don't have just, you know, your house, your living room completely fully lit or completely dark, but you can have any level of ambient light that you want in between fully lit and completely dark. And so it gives you this additional piece of capability. In the case of the qubit, it gives you an additional amount of information that you can encode these kinds of both on and off, both 0 and 1 simultaneously. This also connects back to the Schrodinger cat pictures. Somebody asked a question earlier about, you know, shouldn't one of those cats statistically be dead? And the answer is yeah. Yeah, so it's a very strange, non-intuitive part of quantum physics, that these kinds of basic elements can exist in two kinds of simultaneous situations at the same time. It's also, I'll point to our logo up here in the upper right hand corner. This picture on the right of these two circles with arrows on them is to highlight this encoding of two pieces of information, one that's on and off, and the overlapping of them indicates this idea of being able to be in both of these states simultaneously. So that's, you know, at the very basic level, what the fundamental unit is. If you want to build a quantum computer, you need to make qubits, and there's lots of ways to do this. So let me see. Here are just some of them. So for example, you can make these. You need something that can perform this function, and there's lots of physical ways to do this. So people can engineer circuits that are made out of superconducting materials that can behave like these qubits. This is what IBM does. It's also what the folks at Google do. We work on this at MSU. There's a number of groups working on superconducting circuits that are useful for quantum computers. My group is one of them in particular. You can another way that you can do it is you can take a lattice of diamond here in this bottom left-hand corner, and you can pop out one of the carbon atoms and leave a hole. That's this vacancy. This V is supposed to represent a hole. And then you put a nitrogen next to it, and that thing, the electrons that flow around that that structure, those can behave like a qubit. There are systems where you trap rows of ions in vacuum and shoot lasers at them. Those can operate like qubits. And I want to highlight one kind of stranger quantum computing element, which we're working on. It's very novel here at MSU, along with my startup company, which is called AeroQ, is to use, in kind of an analogy to these trapped ion systems, we trap electrons and then use the quantum properties of those trapped electrons to try to build a new kind of qubit. So those are just some of the kinds of examples. But those are the basic elements. And so the question is, what happens if you put them together and you actually make a quantum computer? And that's what you see here. So these are quantum computers that have been built at IBM. So when Angela showed on that first slide this link to the IBM quantum experience, where you can actually go online and write little computer programs that can be run on quantum computers, you're connecting to machines that look like this all over the world. And so there's kind of a neat feature here. If you look, there's some people here for scale. We're back to room-sized computers again, just like with the early classical computers. And so these machines are essentially the state of the art in terms of superconducting quantum computers that are made right now, but they're very rudimentary. They have at best several tens of qubits living inside of them doing computations. But as you'll see, you can actually do some pretty out there things with even just such a small number of quantum qubits. And if you open up this machine right here, what you find inside is that the quantum computer looks like this. So the qubits actually live here in this bottom region on the right. And all of this other stuff above is apparatus that allows the scientists who work on this to cool those systems down to very low temperatures. So the temperatures that exist inside of these quantum computers are essentially the coldest that you can find in the known universe. And all of these vertical lines and things here, those are wiring that allows you to connect to the quantum computer, the quantum computing elements down at the bottom. So you'll see some pictures from my lab later. We have some machines that look a lot like this. They're a little smaller, but very much in the same spirit. So that's what quantum computers look like, but you kind of also want to think about what's actually exciting about quantum computers? Why do we want to use quantum physics to try to, what kinds of computational things can we do with these machines, hopefully someday? So I'm going to pick two examples. There's a lot of different potential applications. As you'll see, there's a lot of people excited about many of these applications, but two of them that are pretty well established that will be exciting once we have large scale quantum computers are this, on the left here, is the simulation of chemical structures. So I'm showing some molecule that I found on Google. I don't actually know, I'm not a chemist or a biologist, so I don't know what this molecule is, but it's pretty complicated. And trying to computationally solve and figure out what the energy, what the configurational states are of that molecule, what its structure is, what its functionality is, that's a difficult computational problem. And it's difficult because molecules like this are fundamentally quantum mechanical objects. And so they're very well suited to be simulated on a quantum computer. I'll also mention that, this structure is relatively simple, say, in comparison to viruses like the COVID virus that's currently causing the global pandemic. And so being able to solve these kinds of structures and to understand them is something that someday will be useful if we can build large scale quantum computers. That's part of the potential. We can't do it yet, but this is one of the things that people really want to do. The second example is one that a lot of you may have heard of, and that's associated with cybersecurity and encryption. So quantum computers, it turns out, are also really fantastic at breaking currently the best kinds of encryption schemes that we use. So, these are mostly things that we don't interface with actively day to day, but they're important for each and every one of us. Every time you send information to your bank on the internet, that you log into your bank account, or you pay somebody via Apple Pay, or any kind of transaction that involves money, those transactions are encrypted, and quantum computers in principle can break that encryption if we can build a large enough quantum computer. So that's kind of the scary side of things. But people also have ideas about how, there was a question that got submitted yesterday about, are there ways in which quantum computers can maybe make better encryption? And actually, the National Institute of Standards and Technology, NIST, currently is looking into the next. They're involved in making a lot of these standards for encryption, and they're thinking about what's known as post-quantum cryptography right now, and they're actively working to figure out how to protect uh, data and information once quantum computers can be built. And it turns out quantum computers can be helpful for that as well. But those are just two examples. I'll mention, I really want to emphasize this. We can't do these things yet. This is some of the pie in the sky kind of stuff that we want to be able to do with future quantum computers. But I do want to highlight, there's potential, but there's actually some amazing things that have happened recently. So this may or may not be something that many of you have heard about, but it's something that I personally find absolutely amazing. So very recently, this was at the end of last year, there was a race that was put on. It was spearheaded by Google. They have a big quantum computing effort at Google. And what they did is they said, let's come up with a problem that we can race a supercomputer on. So we're going to race against the world's fastest supercomputer. So here on the left is the Summit supercomputer. And yeah, it's the world's fastest supercomputer. And on the right is a quantum computing processor that Google made that has 53 qubits. So just 53. They actually designed this thing to have 54 qubits, but one of them broke. So they actually just ran this with 53. And they ran a computational problem. It's just a essentially a performance metric. They wanted to see, let's race Summit. Let's have Summit and the Sycamore Google processor run the same problem. And the time to completion for the Google processor, it took them about 3 minutes. And most of that time is actually spent sending the signals up and down to the processor itself. And to give you some sense of comparison here, this fastest supercomputer in the world, if it could run this computation, which it cannot, it would take it 10,000 years to do the same computation. So there's a lot of detail about, they actually they didn't run a 10,000 year long computation, but they can estimate how long it would take the computer to run this, and it would take something like 10,000 years. So that gives you some sense of just the disparity. This thing has 53 measly qubits, and actually it was kind of broken, and it still completely outperformed the world's fastest supercomputer. There's a great article in Gizmodo. I've provided the link here that you can take a look. It's a pop science article about this race that was run last year. There's a lot of fun. There's also a lot of fun intrigue because Google did this, and then IBM has a whole bunch of responses to it because they felt like Google was one-upping them. It's a really fantastic story, even if you're just interested in the kind of people part of the story. So, okay, I really want to come back to this one thing. So there's a lot of potential. Quantum computers are super powerful, but if you look at the popular media, there is a ton of hype, and it's important to recognize the difference between the hype and the reality. I really want to, a lot of companies are promising all manner of insanity, and some of it is really great and tied to good science and has like a wonderful amount of potential, but some of it is just hype, and I think it's important to mention that. So that example that I just showed you, on the left here is the hype, on the right is kind of the cold water. So I mentioned, quantum computers are faster than supercomputers. Well, that task, which I didn't say anything about, where they ran this race, is actually pretty made up, and it's not useful for anything. It's really just a proof of concept. So it's not like, a quantum computer can do any kind of computation right now that's at all useful that a classical supercomputer can't do much faster. We're not there yet. So I said, oh great, this is, quantum computers are going to be fantastic for drug discovery, and maybe we can someday simulate molecules that are like this or even bigger. Well, right now the state of the art is we can, on the largest scale simulation that's really been done with quantum computers has been done by IBM, and it's beryllium hydride, which is just one beryllium atom and 2 hydrogen atoms. That's it. So this structure is far simpler than these large molecules. So that's where we are now. But that is constantly getting better. So, quantum computers are going to be great at cybersecurity. That's going to be awesome. Well, actually, in order to really do any of those really exciting cybersecurity things that I mentioned previously, it's widely believed that you're probably going to need millions of qubits to be able to do those kinds of tasks in a meaningful way. Right now, we have 53. So that number is going up, but there's a lot of work to do. And then you'll see even crazier things on some of the on the internet. People are going to be promising you a quantum iPhone or a quantum laptop, or Alexa is going to be powered by AI and quantum together. And I just don't even know what to say about some of those things. That's not what we're doing right now. That's not the right thing to be thinking about. But that being said, the rule of thumb that I take in all of this is it's important not to confuse hype and potential. The potential is real. Like we wouldn't be trying to do these things if there wasn't the potential to actually do something really meaningful with quantum computers one day. But it's important to do the work and actually demonstrate that these machines can work, that they can be better than classical computers. That's the work that needs to be done, and that's what we do. So that leads us to the question, well, what's holding us back? What's the work that we actually have to do? Well, a big important part of all of this is that quantum computers are noisy. So what I mean by noisy is everybody, if you had a TV that had like rabbit ears, you can get into a situation where you're trying to watch your favorite show, and the signal goes completely away, and you get a staticky screen full of noise. So that's a sort of the way in which quantum computers are behaving right now. They're very, very noisy. Another analogy that you can have is, imagine that you're trying to, this one I like because it's communicating information has to happen in a noiseless environment. So imagine you're sitting with your best friend at your favorite French restaurant, and you're trying to have a conversation, but it's like just way too loud. So you're trying to communicate information, but the noise in the background is just preventing that information from getting across. So the qubits that exist in these processors right now, they try to talk to each other in order to do these computations. But the environment that they're living in is very, very noisy, and they're very sensitive to noise. And so that's why we, in the superconducting circuits, we have to cool them down to very, very low temperatures in these massive machines in order to get them to try to quiet away all of that background noise. And so that's a big problem. There are other problems, but this is a real fundamental bread and butter problem that has to be solved to make quantum computing really make that next step. And that's actually a big part of what this center that Angela and Andrew and I have put together here at MSU. So the center is, Angela mentioned this previously, it's the Center for Quantum Computing Science and Engineering. There are about 25 faculty at MSU that are a part of this center, and they're working on all kinds of parts of quantum information science and quantum computing, experiments, theory, developing quantum algorithms, trying to understand the applications of those algorithms to problems in chemistry, nuclear physics, all kinds of things, data science. There's a whole bunch of, so you can imagine this is a pretty complicated problem, right? I'm a physicist. I don't know anything about data science. And so, but being able to interface with collaborators and colleagues from a variety of different departments and being able to do this in a multidisciplinary way allows us to be maximally effective, because everybody brings the things that they're expert in to trying to solve these kinds of problems. And so we have physicists, chemists, we have people from Andrew's department, the computational mathematics, science and engineering department, electrical engineers, mathematicians, material scientists, all trying to do this. So you can see here, and these are just some images from the kinds of work that various of these people are doing. We've got people working on drug discovery and chemical simulation here with these fancy molecules in the middle. This picture of, you can see these quantum computers that are living inside of in my lab here. You can see they look a little bit like IBM's, but a little smaller. Actually, some of it's, I would say, cooler, but whatever. And another important part of this is, it's not just a bunch of professors doing this, there's the grassroots and the foundation of this are the actual people that get into the labs and write the code and run the experiments. And those are MSU postdocs, graduate students, and undergraduate researchers. Those are the people that really move the needle day to day and are thinking about the hard problems associated with how to make quantum computers better, how to reduce the noise in these systems, and really moving it forward. So if you take nothing away from, about the center, except for one thing, remember this: what MSU-Q is trying to do is we're trying to improve your quantum reception. We're trying to limit the noise. So the way that we do that involves, here's some other cool images of the research that is going on, is it requires making new devices. It requires making new kinds of qubits that, that are less noisy or are less susceptible to noise and interference. It involves creating new computer languages. And these are just some of the areas in which MSU is really leading the way, in developing new kinds of quantum diamond qubits. So I'll say a little bit more about that. Developing new programming languages down here in the bottom. My group and our startup company is developing these new kinds of qubits that are hopefully going to be really well protected from noise based on trapped electron systems. And we have people working on a variety of superconducting devices, very much like what IBM and Google do. And in fact, we partner with collaborations with both of those companies, and I'll say a little bit more about that later. So I just want to pick out one example and say a little bit more about some really cutting edge, very unique research that's happening at MSU that's related to quantum computing, making better qubits and making better quantum sensors that are protected from noise, and that are hopefully going to be like the next generation of quantum technologies that we develop. That there's a saying that diamonds are forever. Well, really, quantum diamonds are forever. They're the only ones that really last forever. So at MSU, there's a rich history of working on ultra high purity diamond for electronic applications, and essentially making the world's best diamond. Happens at MSU in partnership with a Fraunhofer Center on campus. And so there are people at MSU, and they're part of MSU-Q, who can make essentially the best defect-free diamond that has ever existed. And we have some of the world's leading expertise in ultra-fast lasers, and you'll see how these two things fit together in just a minute. So we have folks who have been at the forefront of like controlling chemical reactions using ultra-fast pulses of laser light. This is a picture of one of the MSU-Q members, Marco Stantis. He's in chemistry. And if you put these two things together, if you put diamond and ultra-fast lasers together, what you get at the end of the day is quantum grade diamond, that you take these laser pulses and you shine them onto this very clean diamond, and you can create these kinds of structures that I mentioned previously, where you have a qubit that's based on an atomic structure within the diamond. And you can do this in a very reproducible way, and create arrays of these structures on a chip, and then that's essentially the idea. And then these have the potential to be really well-controlled qubits that are very protected from noise. So, for example, the quantum computers, the quantum qubits that are developed out of these, they're called nitrogen vacancy centers in diamond, actually can be operated at room temperature. They don't require those really cold temperatures that are required for superconducting quantum computers or other devices. They're also really fantastically sensitive to their environment. And so people are really trying to develop next generation sensors for all kinds of things. So like sensors for sensing really faint magnetic fields and geopositioning on the Earth, or for biological sensors. And so in addition to the quantum computing parts, there's all these really fantastic sensor things. And MSU is really uniquely positioned to really push this effort forward. And it really came about within the last, year-ish timescale that all of these people coming together, talking, realizing what expertise they have, realizing that they could work together to, really move the needle. And somebody, I mentioned previously, it's an interdisciplinary effort, but it also is it's a global effort. It's not just MSU, and it's not just universities pushing these kinds of things. Somebody asked about whether we have partnerships with and collaborations with the major players in the private sector, and in fact we do. So we have strong collaborations with IBM-Q. We've had very fun workshops in conjunction with them, learning how to use having MSU students and postdocs and graduate students learn how to use their quantum computers at these workshops. We have strong scientific collaborations with Google. Actually, one of the people that I forgot to mention when I brought this up was there's a rich history of quantum computing at MSU. And one of those folks is Professor Mark Dickman in the physics department. He's a very great colleague of mine, but he interfaces strongly with the Google team, and many of the things that he did, he was really at the forefront of quantum computing, 20 years ago, and anticipated many of the problems that the machines that Google and IBM are currently using. He knew those problems were going to be there, 15, 20 years ago. And so he interfaces strongly with their teams to try to help them. I'll mention that, companies that you might not expect to be interested in quantum computing have internal quantum computing teams. So we have a great collaboration with the quantum algorithm team at Ford Motor Company. They have a separate internal division looking at how quantum computing and quantum technologies can help their bottom line. Similarly, Goldman Sachs has a really fantastic quantum algorithm team, and they're working on scientific problems associated with optimization for financial problems. But yeah, it's a really, it's probably the most fun and interdisciplinary part of my job, is interfacing with these people that come at this problem from so many different perspectives and with so many different goals in mind. It's pretty amazing. I never thought, if you'd asked me 10 years ago if I would be talking to folks at Ford Motor Company about quantum computing, I would have, I don't know what I would have said, but I don't think I would have said, oh yeah, that's for sure going to happen. But it for sure happens.
So Johannes, one of the questions that came in is,
oh, great.
Isn't Microsoft working on this too? And where does their research fit in?
Yeah, so Microsoft is actually, Microsoft fits in fantastically. They're trying to make a very strange kind of qubit called a topological qubit. They don't actually even have a qubit yet. They're trying to build one for the first time. In principle, their kind of qubit is very, very well protected from noise, but it is it's tricky. It involves these very funny fundamental particles called Majorana fermions, and it's a work in progress, but they have a very strong quantum computing effort. They also actually interface with a lot of the other companies. What's been happening recently is that there are kind of these tendrils of collaboration that are reaching out from the different companies to each other and to the universities. They're doing some really fantastic work there. Actually, before I came to MSU, I was a postdoctoral researcher at Caltech, part of an institute there called the Institute for Quantum Information and Matter. And for the first maybe half of my postdoc, I was funded by a Microsoft grant to work on topological systems. But that seems like so long ago now. They're doing great stuff. Is that get at the heart of the question?
I believe so.
Okay.
Are we ready for, there's some questions coming in. I know you guys can see them, so I don't know if you want to tee them up as appropriate.
Let me.
Or Johannes, I can ask them. They're also wondering if DARPA is working on this, and I can answer that one. So I previously was head of the chemistry division at the National Science Foundation 2 years ago, while still at MSU, and we actually had meetings with many of the different agencies, and all the agencies are invested in really trying to push towards quantum computing and addressing the major scientific and technological changes. And so, and the different agencies are talking a lot to companies, they're talking a lot to universities. And so this is really a very significant national and international effort. So indeed, DARPA is certainly working towards this. Johannes, another question here is that, will MSU explore the use of antimony in your quantum computers? Is using an antimony a breakthrough?
So the only place where I know that, this is sufficiently outside of my area of expertise. So there are topological systems that use antimony in them. So like Microsoft has, I believe, there's some colleagues of mine at Purdue who are looking at making two-dimensional semiconductor systems that have these kinds of topological qubits in them. When no one at MSU is, to my knowledge, working on this. I believe there are, so I'm going to talk a little bit off the cuff here because I know enough to say something and probably say it wrong. So I mentioned that there are these nitrogen vacancy defects in diamond. There are a whole host of other kinds of structures that one can make in diamond. I know you can use other things other than nitrogen.
Silicon.
And silicon is one.
Silicon.
Thank
Yeah,
you,
there was a
Angela.
paper that just came out on this in Science a couple days ago, earlier this week.
Yeah, so some of the folks who are really expert in this at MSU, I can tell you some of their names. So there's Timothy Grotjohn, he's a professor in electrical engineering. There's Elias Garrett, he is and in material science, and those folks are really thinking about what kinds of other defect structures can you make in diamond. I don't know if antimony is one of them, but that's one place where I would be curious. I simply don't know well enough.
Right. This recent paper had suggested that it could be quite useful, but what's interesting in terms of quantum development is that no one really has the answers, and so that's why there's all these different ways of making qubits that have emerged and continue to emerge, and so people are trying all kinds of things to see what kind of technology is really going to work out, and particularly we've got these really super cool type qubits, and some of the stuff that Johannes is doing and some people at MSU trying to come up with qubits that don't require this extensive amount of cooling. And I think I'm hoping that we'll have some continued breakthroughs in that area, because that is, I think that's an important step towards the future of widespread quantum computing. Actually, Johannes, another question has come in.
Yeah, I see it.
Yeah, can you discuss the interface of the
Absolutely.
operating system?
Yeah, so somebody asked, can you discuss the interface of the operating system and the qubit? This is a great question, and there's many different levels. So and it depends, the different levels depend on what kind of quantum computer you're working on. So I'll take, for example, just say a superconducting quantum computer like the ones IBM and Google have in those big low temperature systems. So at the basic element is a little circuit that is the qubit. The way that you interface with that at the first level is through a series of microwave lines. So you send microwave signals down to talk to that qubit through just coaxial cables that are in the cryostat. And then beyond that, at room temperature, you have to create those microwave signals. So you have to make all of those pulses. And then that microwave generator has to interface with a classical computer. And so the interfacing happens there, but there's all kinds of, so that's kind of the hardware level. But then you don't want to be, if you're writing a program like for IBM's quantum computer, you don't want to interface at that level. That's like, the machine code essentially of, you don't want to go and punch your own holes in the card. What you want to do is have some interface, and IBM and Google have invented some of these. So IBM's is called Qiskit, and Google has one called Circ, and they are front ends that essentially allow you to, you just tell the quantum computer essentially what it wants, what you want it to do, and then that does that controls then the hardware in the quantum computers. But that's actually an area of development. So building those kinds of interfaces and building essentially how the hardware couples to the software stack is an open problem that many companies so there are some companies who are working on just that, like how to make that kind of software and make those interfacing systems. There are some companies which are full stack and they're working on just like every level of quantum computing from hardware to, application. There are some that are working on just hardware. It runs the gamut.